Okay, so let us begin this lecture. So in the previous lecture we had studied the notion of a closed subset. We had introduced the notion of closed subset and closure of subset, and we also saw in the exercises that the closure of a subset A is the smallest closed subset which contains A. So let us continue our discussion with closed subsets. So today we will begin with the definition of a dense subset. So okay, so as always, X is a topological space. So let a subset T contained in X is said to be dense in X if for every non-empty open set U contained in X, we have T intersection U is non-empty. Okay, and the proposition, the main proposition is let A be a subset of X and let A closure denote its closure, right. So let A closure have the subspace topology then A containing A closure is dense. Okay, so let us prove this. So we need to show, so by the definition of denseness, so we need to show that if V contained in A closure is a non-empty open subset, then V intersection A is non-empty. Okay, so by the definition of subspace topology, so by the definition of subspace topology, this set V is equal to U intersection A closure for some open subset U contained in X, for some U open in X, right? And as V is non-empty, this implies there exists some X in V which is equal to U intersection A closure. Yeah. So therefore, U is an open subset of X and U contains X and X is in A closure, right. So thus by the definition of closure, this implies that U intersection A is non-empty. Recall the definition of closure, X is in A closure if every open subset containing X meets A, right. So this implies that U intersection A, which we can write as U intersection A closure intersection A, because recall that A is contained in A closure, that is trivial, and this is equal to V. This is non-empty, right? So thus V intersection A is non-empty, right? And which shows that A is dense in A closure. Okay, and so let U be open in X and V be open in U, where U has been given the subspace topology. Okay, so then we want to say that then V is open in X. Okay. So in simple words, open subset of an open subset is open in the larger topological space, right? So let's prove this. The proof is easy. So by the definition of subspace topology, there is an open subset V tilde in X such that this V is equal to U intersected V tilde, right? But now U is open in X, V tilde is open in X, and finite intersection of as both U and V tilde are open in X. This implies U intersection V tilde, this is equal to V is open in X. So this completes the proof, yeah? So this completes the proof. Okay, and similarly we have a similar result for closed subsets. So okay, before we prove that result for closed subsets, we need a small lemma. Let A contained in X be a subset. The closed subsets of A, where A is given the subspace topology, yeah, of A in the subspace topology, are precisely of the form Z intersection A, where Z is closed in X. So let us prove this lemma. So the open subsets of A are precisely of the form U intersection A, where U is open in X, right? And the closed subsets are the complements of open subsets here. So thus, closed subsets of A are precisely of the form A, and we remove an open subset, right? So now a simple say theoretic check shows that intersection A. Yeah. Right? But x minus u is a closed subset of x, right? So thus are precisely of the form Z intersection A, where Z is a closed subset. So this is our Z. Okay, and as a corollary of this lemma, let us see the analog of the proposition, which says that closed subset of a closed subset is closed in X. So let Z be a closed subset of X. And let Z1 be closed in Z. Okay, so then Z1 is closed in X. Right, and the proof of this corollary is very similar. So by the previous lemma, this subset Z1 we can write as some Z tilde intersection Z, where Z tilde is a closed subset of X, right? And as the intersection of closed subsets is closed, so as intersection of closed subsets is closed, this implies Z1 is closed in X. Okay. So next we want to say that checking whether a subset is closed or not can be checked by restricting our attention to closed subsets. So precisely what I mean is the following. So let Z1 and Z2 be closed subspaces such that this X we can write as Z1 union Z2. Okay, so a subset Z containing X is closed if and only if Z intersection Zi is closed in Zi for I equal to 1, 2. Okay. So this proposition will have a useful corollary, which we will see next, but let's prove this proposition first. So if Z is closed, yeah, then simply because intersection of closed subsets is closed, so this clearly implies Z intersection Zi is closed. Okay, or by the lemma, yeah. So then by the lemma, so okay, so let me just write this implies that intersection Zi is closed in Zi. Okay, because this earlier lemma, because of this lemma, right? Okay, and so let's prove the converse. Conversely, assume Z intersection Zi is closed in Zi for I equal to 1, 2, right? So then by this corollary, because of this corollary, right, Z intersection Z1 and Z intersection Z2 both are closed in X. Right. So then by the above corollary, so let me just keep the corollary here. Z intersection Z1 and Z intersection Z2 are both closed in X. Right. And since the finite union of closed subspaces is closed, so this implies that Z, which is equal to Z union Z1, I'm sorry, Z intersection Z1 union Z intersection Z2, right, as X is equal to Z1 union Z2, right, and finite unions of closed subspaces are closed. This implies Z is closed. Right. So as a corollary of this proposition, let's prove the following useful result. We have the following useful result about continuous maps. So theorem, let A and B be subsets of X such that be closed subsets such that X is the union of A and B. Okay. So let A and B have the subspace topology. Okay. Now let F from X to Y be a map. So right now it's just a map of sets such that F restricted to A and F restricted to B are continuous. Right? So then F is continuous. So what do we mean by F restricted to A and F restricted to B? So look at this inclusion. So let's call this I sub A and this is F, right? So F restricted to A is simply this F compose this inclusion lines. Okay. So if F is continuous, then since both the inclusions are continuous, obviously the restriction is continuous. So here this theorem is telling us that if the restriction of F to both A and B is continuous, then F is continuous on X. Right. So to check that a map is continuous, it suffices if we can write our topological space X as a union of two closed subspaces, two or finitely many, and such that F restricted to each of these is continuous. So we will only prove this for the union of two closed subspaces, but it will be immediately clear that the proof works for finitely many. So proof, right? So to show F is continuous, enough to show that F inverse of a closed subspace is closed in X. Right. So by the previous proposition, it is enough to show that f inverse of y prime intersected A and f inverse of y prime intersected B are closed in A and B respectively. Right. But note that f inverse of y prime, this is a simple set theoretic check, intersected with A is simply f restricted to A inverse image of y prime, and similarly f inverse of y prime intersected B is equal to f restricted to B inverse of y prime. Right. So as f restricted to A and f restricted to B are continuous, so this implies that f restricted to A inverse is closed in A, and similarly f restricted to B inverse of y prime is closed in B. Right. So this implies that f inverse y prime is closed in X. This implies f is continuous. Okay. So as an application of this proposition, so use this theorem to show that the maps. So we have two maps, let's say f1 from R2 to R, f1 of x comma y is equal to the maximum of x comma y, right, and f2 of x comma y is equal to minimum of x comma y are continuous. Right. So so write R2 as a union of two closed subspaces, and F1 and F2 both restricted to each of these subspaces should be continuous. That should be trivial, and therefore both these maps are continuous. Yeah. So we will end this lecture here.